So let's get started. Just quick introduction. My name is Chester Chen. I'm the organizer for San Francisco Big Analytics. We are the meetups started in 2015, so we approximately hosting meetups once a month. So the topic usually around the data infrastructures, AI infrastructures, and machine learning related stuff. So today we have a special guest, Zvonko from NVIDIA. He's our principal engineer, especially working on this Coco project. It's a computational container for GPUs. As everybody, a lot of people already know that computational computing is very important, and combined with any other than AI technologies to become ever increasing important for many industries. So we ourselves have been working with this on this direction as well. So I thought it would be very timely and interesting to have Zvonko to give us an introduction what this computational container project is, especially with GPU. Without further ado, Zvonko, please take over.
Great, thank you, Chester. Yeah, as Chester already said, I'm with NVIDIA. I'm working in the cloud native team, and my main responsibilities are leading the Kata and confidential container stuff at NVIDIA. And yeah, today I want to give a overview how we got to confidential containers, why we settled on Kata, how we enabled the GPU, what we added upstream to create a virtualization reference architecture, how we are leveraging confidential containers, and as an example, what can we do like with confidential containers in the scope of a confidential RAG LLM. So let's start first by defining what a container is. Essentially, it's just a process with namespace separation and C groups resource management, right? Containers, the biggest weak point of containers is that they're sharing the host kernel, and they're relying on the underlying kernel the system calls. It's just a modern way of packaging, sharing, and deploying an application. What we have with containers is user space abstraction only, which means we have a weak security boundary from the container runtime to the host operating system. There are other functionalities like SLNX AppArmor for the host to create more container isolation, but they are not enough to create a secure environment for running workloads. As I said before, we are highly dependent on the kernel. So if something breaks in the kernel, we are affecting the complete node. We don't have any hardware isolation. Host changes can break the container stack, and especially the accelerator stack in particular, because we are relying on kernel modules and other parts in the stack. A container escape can take over the whole node, can take over the complete cluster, even the complete site, depending on how much traversal is the attacker able to do. And the other thing is we need to trust the container image provider and manifests. We are naively just doing a Docker run hello world, Docker run Ubuntu, but who is guaranteeing us that this image coming from those repositories are genuine, are in the state that we are expecting it? So there are a lot of attack surfaces. Why a container is not the proper isolation technique to secure a workload. In the past, there have been some attempts to fortify the isolation between the container runtime and the host operating system. There are things like unikernels, which is essentially a kernel package with the user space. So you have just one binary blob that you're running. They have fast boot times, small attack surfaces, and you have a smaller latency, but moving legacy applications to unikernel is very hard. And from our community, we have some folks that are working on unikernels. So if you're interested in that, there's a link down in this slide for how unikernels can be used, for example, Knative. Moving forward, IBM introduced IBM Nabla, which were unikernels as a process. So they are reducing the amount of syscalls, hypercall, and adding hypercalls to emulate some dangerous syscalls. They even added a OCI compatible runtime, which was called run on NC. So you could run unikernels in a Kubernetes setup. They made it easy to build those unikernels, but this really didn't took off because of the overhead of transforming your current workload into a unikernel. Google come up with gvisor, which is essentially a user space kernel. And what I've done, they re-implemented syscalls. This is essentially a kernel in user space. So every syscall that the container runtime is doing is filtered by gvisor, and gvisor has its own implementation of all those syscalls. Another project is KubeVirt. And KubeVirt is a full virtual machine, a full-blown operating system, and QEMU VM running in a container. It's mostly used to run legacy VMs. So if you have an old VM application you want to run natively in Kubernetes, you can use KubeVirt to easily map it into a Kubernetes environment. It's a VM running in the container, so the pod is just the deployment vehicle. You still need to interact with the VM with the old tools. There are some abstraction to use this, but KubeVirt is not really compatible with all the Kubernetes interfaces like CNI, CSI, and CRI. AWS created Firecracker. It's a Rust-based VMM. It's based on KVM, which is the hypervisor. It's a micro virtual machine with a minimal operating system and emulated devices. They still don't have any GPU support because Firecracker does not have a PCI Express topology. But they were thinking of how to integrate GPUs into Firecracker. And lastly, we have Kata containers. And Kata containers are pods running or containers running in a VM. Those are micro and light virtual machines that have hardware virtualization and hardware isolation. And why we use Kata containers for moving forward and how we implemented it, confidential containers, will be presented in the next slides. It's a container in a VM. Kata supports a broad spectrum of hypervisors, so you can run Kata with Firecracker, with QEMU, Cloud Hypervisor, Acorn, so it's completely pluggable. Kata seamlessly plugs into existing orchestration platforms like Kubernetes and other container runtimes, be it CRI-O, Containerd. The nice thing is about if you're packaging your user space workload into a VM, now it becomes kernel and user space independent, because host kernel updates cannot easily break your stack because you're running your own guest FS and own guest kernel, which enables us to run untrusted code in a container because we have the virtualization as a second line of defense. Main architecture of Kata is we have an outer runtime, which is used to lifecycle the VM. And then we have an inner runtime, which is talking to the outer runtime to manage the containers running inside of the VM. And additionally to KubeVirt, Kata is fully OCI compliant, meaning you can transparently plug Kata into Kubernetes and it will support any of those interfaces, be it the storage interface, the networking interface, or the runtime interface. Besides hardware isolation, there are, of course, other technologies to fortify the isolation. I'm not going to go very much into details here, but we have homomorphic encryption, we have secure multi-party communication. And the last thing that evolved out of those fortifying the isolation were recently the trusted execution environments. Those are not very new. One of the first was by Trusted Logic in 2004, and then we have like things like TrustZone in 2006. Then came SGX, which is a process-based isolation. SFV started with the VM isolation, encrypted VMs. Then we got Nitro enclaves, and then recently we got TDX, SFV, SMP. ARM v9 will have CCA support, which is the trust execution environments equivalent for ARM, and RISC and has CoV. And on S390, on the mainframe, we have secure execution, and on Power, we have similar trust execution environments. So let me go over on the Kata containers and why, how, and what we are doing upstream. I said before, we are now kernel and user space independent. Container breakouts cannot compromise the whole node or the complete cluster because, again, we have the hardware isolation as a second line of defense. We are seamlessly plugging into existing orchestration platforms. We can run untrusted code in a container, and we are supporting with Kata a wide range of trusted execution environments, be it TDX, SMP, SC, or CCA. So all the major companies or CPU vendors are working upstream to enable Kata with all their trusted execution environments. Upstream, we are collaborating with many companies, be it Intel, AMD, ARM, and we have architecture committee meetings. We're discussing like the future of Kata. We added for, especially on the PCI Express topology, we added the reference architecture for virtualized environments. I have some slide later on what this means that we can use as a blueprint for other VMMs, be it Cloud Hypervisor or Dragon Ball, which is the Rust implementation used by Alibaba, similar to Dragon Ball, for having a micro latency sensitive VM to run, for example, cloud functions. And that's how Alibaba is leveraging Kata. AWS has also support for Kata. So if you have a Metal instance, you can deploy Kata on AWS. We are reusing parts of our cloud native stack that we already have for the GPU enablement, be it CDI, which is the container device interface, NFD, node feature discovery, device plugins, host driver containers, and lastly, the GPU operator, which is our deployment vehicle to enable the GPU on traditional containers, but we are using the very same components with Kata to enable VM-based or confidential containers. And we are also extending the cloud native stack for any sandbox environment for seamless integration. So currently we are supporting like Kata, KubeVirt, Firecracker, so we can run most of the VMs out there with Kata or with KubeVirt, and it's all supported by the GPU operator. What we've done so far is to enable like GPU and NIC pass-through and accelerators in general, like all the VFIO handling, the vGPU and Mellanox NIC support. We're extending the Kata's PCI implementation to support like host topology replication or side channels to provide meta information for use cases like GPUdirect RDMA or GPUdirect storage. There are other things that we are doing to the cloud native stack, like extending NFD to expose more information to the cluster, to detecting exposing TEs, and for using it mostly for sophisticated scheduling decisions. Also creating like various runtime configurations for the GPU and NIC, and it's always a set of kernel guestfs and configurations per pod. One important thing maybe to say is that per pod, we can change the PCI Express topology and kernel guestfs on the fly. So for each pod, you could have different guest kernels, different guestfs, and different PCI topology, which makes it easy, let's say, to run one pod with GPUdirect RDMA support, the other one with GPUdirect storage, and the other one, let's say, only with a CPU. We're adding more features like inter-VM communications, VTPM support, so that we can protect the measurements that we're doing in there for IMA or EVM, which is the file integrity mechanisms of the kernel. And really the end goal for Kata is to able to run GPUdirect RDMA or GPUdirect storage in Kata containers in virtualized environments. So let's move on and let me explain a little bit about our GPU container enablement stack. One premise we made from the beginning is we wanna have the lift and shift characteristics. So one premise was no code modifications to our GPU stack and Kata and Coco, so that customers can use their CUDA workload and run it on Kata or on a confidential container. What we're essentially doing is for each container, we're providing the needed libraries, binaries, and tools inside of the container with CDI, which is a technique that we recently added to major runtimes, which works with all major runtimes like Docker Containerd, CRI-O, and it works on GPUs, be it Jetsons, Orin, or all the enterprise GPUs. There are two links if you're interested how those things are working in detail from colleagues in the team that are going over all the Kubernetes related stuff. Just wanted to showcase how the stack looks like, because this is important later on when we are going to describe how we enable it in Kata. As I said before, we have the GPU operator, which is the one-click installation, lifecycle management on Kubernetes, deploying all the needed tools, the device plugins, the discovery, the driver containers, and then lastly, like the GPU application. So we wanted to keep our hardware reference enablement for Kata as well, to keep the lift and shift characteristics. So a customer should have the same feel if they are running a traditional container, a Kata container, or a confidential container. Our stack is tested in production for many years. We didn't want to reinvent the wheel. Let's reuse what we have. And really what we've done is just use the bare metal enablement stack and push it into the VM, which means we are reusing the container enablement stack. It's completely hypervisor independent because the enablement is done by the container runtime and not by kind of the VM. And what we're doing is applying like all the needed GPU artifacts to enable this, which means you can run a CUDA container unmodified in a Kata container. And we have different runtime configurations for different use cases, because for GPUdirect RDMA, you need more drivers, so you don't want to have a full-blown or bigger guest FS. You may want to minimize also the attack surface on your guest FS and on the kernel to be as minimal as possible. Okay, one big part that we added was the virtualization reference architecture. If you're looking at all the use cases that we have like physical functions, we have virtual functions, we have mixed slicing, we have the NICs that also can be configured as a PF or a VF. And so there are a lot of use cases that we want to enable. And the main point is the driver stack will disable peer-to-peer, so the communication directly between a NIC and a GPU if your PCI topology is not suitable. There are a lot of factors that we need to consider, like IO, MMU, ACS, ATS, and all the other buzzwords that I'm laying out there here. And then we have hardware constraints like Luma and CPU sockets. So essentially what we added is like two modus operandi that we can be reused for any VMM. This is like our host topology. We have Mellanox NICs and a GPU under a PCI Express switch. So the first thing that we can do is flatten the hierarchy. This is what most CSPs are doing, like vSphere, Azure, GKE, or AWS, is just attaching all those devices, those pass-through devices, behind a PCI root port. The thing is, we are losing the topology information here, so we need to add meta information saying which devices are capable of peer-to-peer. And this is important for libraries like Nickel. They need to know which peer-to-peer level they can leverage for IB or UCX. The problem is here, low-level software like IB verbs directly using IB verbs is not capable to deduce anything from this topology. So we needed another way also how to express the host topology in virtualized environments. Yeah, this is just an example that we can hot plug GPUs or cold plug GPUs to the root port. And this is also can be done per pod, so you can decide how you want to create your topology per pod. Let me see here. Yeah, GPUdirect just reads the PCI config space. There is a capability in the PCI Express config space that you can add as a meta information. It's essentially a click ID or a group ID where you're saying which two devices can talk to each other. So the problem is how we are going to provide this transparently in a cloud native way, which was one of our challenges, rather than adding some meta information that's not vendor agnostic. So coming back to the CDI, which is the container device interface that we are working on upstream, we can add meta information and say, okay, this GPU and this NIC are belonging together. Please enable peer-to-peer. And you can, and Kata will deduce all the needed information of all the verifier devices, and it will enable peer-to-peer communication inside of the VM. Coming back, remembering this topology, but it would be also nice if we could just replicate some parts of the topology without adding like more meta information. And this is like the second modus operandi that we added. You can just replicate parts of the host topology stack that you really need inside of the pod. So you have, again, a switch, and you have downstream, you have the GPU and the NIC. So the driver stack does not need to deduce any additional information. It can just enable peer-to-peer because there's a switch. We know we added like enabling of ACS and other stuff. And the driver stack can just use the topology to directly enable peer-to-peer. There are some other things that we need to set, but it's far more easier for the stack to enable peer-to-peer here. Yeah, there's some also, if you're working with VMs, there are limits that we can do. This is an example for QEMU. We cannot, there's a limit on the number of PCI root switch bridge ports, like 32 slots on the PCI root bus. In some, we only have 256 slots. We can only enable like 16 root or switch ports. Yeah, and there are some other intricacies. For example, you're not essentially passing through a GPU, you're always passing through a whole IO-MMU group. And some consumer GPUs have 4 devices per IO-MMU group, which means if you pass through 8 GPUs, you get a problem here because you don't have 32 root or switch ports. So what we added also is some meta information that we are saying, okay, please attach the GPUs to the root port and attach all the non-needed pieces to the PCI Express PCI bridge, which is essentially a don't care. So we can eliminate pieces from the IO-MMU group and attach it to non-needed parts of the VM. Right, so we added all the features in Kata. We added the virtualized reference architecture, meaning sophisticated use cases like GPUdirect enabled in Kata. Now let's take the next part that we need, which is the confidential GPU. And confidential compute on the GPU didn't happen like from one day to the other. It even maybe started before 2018, but I'm just highlighting here some of the things that were added to the GPUs, like firmware authentication, encrypted firmware, secure boot on the GPUs. And then with the H100, which is the first confidential compute GPU, there is a on-die root of trust where we can do measured boot, and it has FIPS level 2 certifications. Additionally to the H100, the Hopper, the Blackwell that was announced recently, it adds TDISP IDE. So I need to say that the H100 is using bounce buffers to communicate with the CPU. And those are encrypted by the GPU and by the CPU. It's not encrypted by the PCI Express bus. And the TDISP IDE, which is PCI Gen 6, adds native encryption and decryption support and attestation on the PCI Express level. So the CPU and the GPU don't have to do any special handling, and we can eliminate like the bounce buffers that are used in the Hopper GPU. Again, as I said before, no code modifications as well for confidential containers. Just use your workload, run it on Kata or a confidential container. Oh, confidential containers is just an umbrella term for Kata and some additional guest components. Those guest components include attestation and other parts. I just think, yeah, like secure storage or sealed secrets for unsealing it inside of the VM. So essentially, the big part of confidential containers is Kata. That's why we invested a lot in Kata, enabled like all the features for the GPU. Again, we are reusing again the complete enablement stack that I showed before in Kata now, which are more targeted. And the confidential use case, again, we added more runtime configurations for confidential. We had runtimes already for the Kata use case. Now we are just adding those runtime configurations for the confidential use case. I mentioned before attestation. So one big part of confidentiality or confidential computing is attestation. And this is proving, let's say, to the workload owner that a system is in a specific state with, let's say, specific versions that I'm expecting, specific settings that I'm expecting from the GPU or the CPU. So essentially, you are requesting a report from the hardware telling you what the hardware has measured in a secure way that you are comparing with gold measurements. And then depending on the difference between your gold measurements and the measured values inside of the hardware, you have a policy where you're saying like, okay, if this component is higher than whatever else, you can say, okay, I'm denying the execution of my workload in this hardware because I'm not trusting you, because my gold measurement tells me firmware version should be 1.2 and you're giving me 1.1, right? So this is a big topic when you're running confidential workloads. And NVIDIA is following the RADS architecture. I added links here if anybody is interested how this all works. But so essentially, it's always the same workflow. You as the relying party request reference value from the hardware that you're comparing to your gold measurements, and then deciding upon a policy if you are allowing to run your workload inside of the VM. What enables a attestation as with confidential containers is secure key release, meaning if we know that our hardware and software is attested, we can release secrets into the confidential container, maybe to decrypt a model, maybe to decrypt some storage that we can use because we know our hardware software is attested. We know it's running in the right version, in the right configuration. We can release the key into the CVM or in the confidential VM or the confidential container, and then we can access like our confidential storage. The right part is the project that we upstream call Trusty, which handles the communication with the confidential container, which includes a key broker service, attestation service that can broker out to, let's say, the NVIDIA remote attestation service or to the Intel Trust Authority, which is the remote attestation service by Intel. Usually this runs like on the tenant infra or the workload owner infra. So your gold measurements are on your infra, and then you are testing it against a CPU, GPU where your workload essentially wants to run. If we take all those parts, this gives a brief overview of all the deployments model that we can do with the GPU operator on a cluster. You could have one node with traditional containers where the GPU stack is running to enable like the normal pods. You can have a node with confidential containers where you're doing like the GPU PF pass-through, or you can even have a node with Kata containers where you're not doing any confidential compute, where you may be also even running KubeVirt or other workloads or other isolation techniques. So all of those use cases are supported by the GPU operator. with other components that are coming from the cloud native stack. And how do you enable, or how do you go from a traditional container to a confidential container or a Kata container? It's just by annotating or setting the runtime class name in your pod YAML with the specific runtime that it's deployed on the cluster. Here as an example, it's Kata QEMU GPU SMP, which means this pod is going to run on a CPU-enabled SMP, on an AMD CPU with SMP that has a GPU, and the hypervisor would be QEMU, right? And if you just want to run a Kata container, you're just using the correct runtime class, Kata QEMU GPU. So that's what I meant with the lift and shift strategy that we pushed from the beginning, that take your traditional container, just add the runtime class name, and you're running it in a confidential container, or change it to another runtime class name, and you're running it in a Kata container. Yeah, and as the last part, I just want to go a little bit as one of the examples how confidential computing can help. This is like the top 10 OWASP potential threats for LLMs. And the threats are on the left side and the potential mitigation are on the right side. Some of those threats can be mitigated by confidential computing, but they are threats like, let's see, where is the, yeah, for example, oh, where's the prompt inject? Oh yeah, number one, right? We can limit like the attack surface or secure execution of plugins, and we can add traceability with, but it will not prevent you from prompt injection 100%. On some things, we can limit the attack surface. We can secure data which is in use, prevent data injection, supply chain verification, and stuff like that. But one thing to remember is if you're running a random script from the internet inside of your confidential environment, it's still a random script that can, copy out data, that can leak data or destroy your cluster. So it will not save anything from all threats, but it can save a lot of, or mitigate a lot of potential threats, especially here for, as an example, if you're running with RAG LLMs. And if you're looking at a simple pipeline, where we have the model server, the vector DB, API server, web frontend, and you're asking yourself, well, what should I run in a confidential container? The simple answer is really run everything in a confidential container, because again, a container breakout can take over the complete node, the complete cluster. At least if you're running it in a confidential container, your data confidentiality is still valid. It's obvious that we want to protect our model, that we want to protect the vector DB, our data sources, where we can use like the secure key release to decrypt confidential data only in the trusted execution environments. We want to protect the API server from injecting any malicious response requests, and the web frontend would need like some kind of attestation that what or where the requests are going to are valid, and all of my sources like the model store vector DB are in a state that I'm expecting it. So essentially, with a confidential containers environment, you can mitigate a lot of threat vectors here, and it really is to enable zero trust in your architecture, because every component could be a malicious attacker. Yeah, closing remarks. Upstream, we have still a lot of work to do. What we haven't solved right now is like how we are doing the attestation with several personas. So how do we realize a data clean room? We have multiple personas like the data owner, infrastructure owner, model owner, clients. How are we protecting each of those that wants to run on the very same in the very same confidential environments. And at every stage of the AI pipeline, we have someone who wants to protect the data, be it exploration, training, or inferencing. Yeah, that's all for me. Any questions?
Yeah, great talks. Any questions? You can post. You can either unmute yourself or directly tap on the chat. Either way is fine. We don't have a lot of people, so you can, if you want to talk, you can just directly ask the question. So maybe I'll ask a first question. So just kind of throw something out. Zvonko, so when these are available, for when people can try it out for some of these, if people want to experiment.
Depends. You can try it out right now if you have a AMD CPU and a H100. There is a tech preview in the GPU operator for AMD SMP. But I must say that one obstacle for adoption is the availability of patches in the kernel. So you still need to build your own kernel for the host, and this is what throws off many people, that they still need to run like their own build of a host kernel. Last time we checked, we should have all the patches in 6.11 or 6.12, and Ubuntu 24 has all TDX patches as the host. So the latest Kata supports Ubuntu 24.04, and RHEL 9 point something will also have all the TDX patches and SMP patches in there. So it's evolving, but you can start to test it today. There are some steps that need to be done manually depending on the BIOS version, on the firmware version of the CPU, but we have documented a lot of those steps upstream, either in the Kata community or on our NVIDIA pages.
Okay, so let me ask a second question. When the Kata container or computational container starts up, I assume there are certain attestations during the boot time will be executed. Is that correct, or is something application need to do?
Two-way. So what we have is pre-boot attestation, meaning the hashes of the kernel, the kernel, the guest FS, and parts of the configuration are hashed in the initial measurement of the VM. So this is the first step of attestation, meaning that we are booting up a valid OVMF, a valid, which is the firmware, a valid kernel, and a valid guest FS. Then we have measured root FS support, meaning we are running DM Verity on the root FS. So we have having a hash of, also creating a hash on the complete root FS system, which is checked at startup. And then the VM starts up, and when the container, we are supporting like encrypted containers as well. And if a encrypted container is requested to run in the VM, the attestation pipeline is kicked off, meaning the CPU is attested, and right before the container starts up, the GPU is attested as well. We are reaching out to the remote attestation service, and if the attestation report is green, we are setting the GPU to ready. That's a new feature in the Hopper GPU. If attestation fails, we are setting it not ready, so the container will still come up because the CPU is attested. But if the GPU is not attested or not valid, it will be not ready, so you cannot run any workloads. So we are still discussing upstream what the right way to do is if parts of the stack are not attested. I think as a tech preview, this is okay just to get started to know what is happening. But maybe we should just deny the complete execution or just shut down the VM immediately if parts of the stack is not valid. But this could be also a policy setting, because let's say you have a long-running job and there is a minor CV that you do not care about, that's not related to you. So attestation may fail because some certificates are revoked. And you're just ignoring it, say, okay, this CV will not affect me. I'm running on-prem. I'm sealed out, and I don't see any way that this can work. So you have a policy to override attestation results. It really depends on the policy.
So the application could retrieve the report, right?
Yeah, not inside of the container. So we have currently a upstream discussion if a container should be able to retrieve a attestation report, because this opens a can of worms on attacks on KBS. Usually all those things are happening underneath the container inside of the VM without the interaction of the actual container running inside of it, because this will also break the lift and shift characteristics, right? If you have a workload running on traditional containers, which has no sense of attestation, and now it's running in a confidential container, now it needs to attest, which is, yeah, but we are trying to enable this interface as well. But customers need to be aware what they are enabling here, because if you can create a valid attestation report, you could reach out to the KBS and maybe switch namespaces if you have multiple personas, right? Because your attestation report is valid. So yeah, give me the key of namespace A. So this is something we are currently discussing upstream, and need to be cautious what we are enabling on the workload level, because this can create some attacks on KBS or trustee or the attestation pipeline.
I see. So that's an interesting point, because we are kind of leveraging that capability to checking, like in federal learning, you're checking the server, checking the client, and client checking the server. So we kind of need to know the others and then get the reports from the other parties to cross-check.
Right, but this could be offloaded to the VM level, right? You could have an agent in the VM that's doing this periodically. It does not have to be the workload doing that. So you could do it on the VM level. And the VM has full access to all the resources. And on the VM level, it will have the policy, and then you can still decide what you're doing with the workload. You can kill the workload, create an alert in Kubernetes, or whatever else, right? So the high privilege operation should be really done on the VM, because the workload has no access to the VM, and the VM has access to all the hardware and can do like those high privilege operations.
I see.
The workload, yeah, you need to, depending on the threat model, you need to see how you are architecting your stack.
Right. So kind of related to that. So the other pieces is as we go through the different use cases and federal learning workflow or multi-party computing use cases, one pieces keep popping up is like we might need to customize certain things, like a key release to certain custom objects or code or whatever, right? So can that be, because that key release need to go through the testation. So is the application able to leveraging the trustee, or, in the future, not right now, but say, hey, I want a custom code, custom key value pair somewhere, but I need to go to the trustee, say, hey, can you retrieve that key for me if you're somehow get that attestation to pass?
Yeah. I mean, if you are the only persona running in the confidential environment, then it's pretty easy. So there's a REST API for trustee, so you can ask for secrets, and this secret is going only to be released if all the attestation has succeeded, right? But if you are multi-persona, this looks different. So we need to add more RBACs or identity management or stuff like that. So this is, as I said before, this is one big topic, how we are doing like the multi-persona in a single confidential environment. If you are alone, if you are the only workload owner, then it's easy. You just ask trustee, hey, give me the key for XYZ. Trustee will check, run the verifiers. If it's not have none, ask their testers to give the measured values and then run the attestation pipeline and say, okay, here's the key. Everything looks good. So if an attacker changes, like let's say underneath doing some replay attacks on your storage, replay attacks on parts of the system and changes the measured value, of course, Trusty will not release it because the measured value do not match the reference value that you have on your side.
Yeah. Great. I think I actually had one question. So it's a really good talk. Thank you. One question. Usually, can rely party ask extra items of measurement? For example, if the only version of the BIOS is tested, can relying party ask for checksum of the BIOS?
The relying party, what would be like so?
Yeah, this is Isaac. Yeah, actually,
yeah.
The question is, usually when the evidence being attested,
yeah,
the entire evidence is predefined.
Yeah.
There is no extra items can be presented to the attester.
Yeah.
So my question is, if relying party say, those evidence is good enough, but I just want one extra more, is there any way that that information can pass to the attester and even to the evidence side, say, okay, please give me one thing more, just one thing more. Maybe the process is currently running for certain file and the checksum of that file.
Okay. Currently, you cannot do this on the fly. You would need to write your own verifier and attester, because so the attester can only create measurements what it's told to do, and the verifier can only check the measurements that it's told to do. So if a tester and verifier does not know nothing about that, so you cannot say or request on the fly specific items. So you would need to create another verifier or tester. But let me think. There is let me think. Yeah, you would need to dissect. Yeah, no, this would be additional, which is not already in the attestation report. Yeah, you would need to extend it. Yeah.
Okay.
You cannot do it on the fly.
Currently
right now.
In the industry, which organization or company or some kind of non-profit organization define the entire items of the evidence? Just take one example. Azure may say, okay, this is all the items that I can retrieve from the hardware platform, and those will be attested. But if we are not in Azure, who else can define the entire items of the evidence? In GPU, we may have several items, but so those are predefined.
Yeah. So yeah, for the GPU predefined, for the CPU are predefined, but nothing will prevent you to extend the attester or the verifier for your use case. So we are this is a good point. So currently, so there's the IETF, different working groups. One of it's RADS, which is the remote attestation architecture that they're building, but they're also working on data structures, exchange formats, attestation reports, how do results need to look like. And like 1 hour ago, we discussed in our community meeting the use of CORIMs. And CORIM is a standard which lets you extend attestation reports easily. So this nicely fits into your question. So we are currently in the process of enabling like the CORIM standard for confidential containers, which makes it easy to extend measurements by self-defined values. Maybe you want to have the hash. If you're saying like a hash could be anything, like a hash over over a guest FS using like DMVerity with a Merkle tree, or a hash of a container, or the hash of your SBOM, or signatures, right? So with this standard, you can easily extend the attesters and verifiers, but someone needs to implement it. And if you need something like this on the fly, then we need to build some mechanisms for trustee or other or attesters and verifiers to enable this dynamically. But that's a good use case. I can bring this up if this is something we want to also enable inside of trustee, because we are also currently looking into ways how to, I mean, the GPU is the first accelerator, but they may be confidential NICs coming in, confidential DPUs, confidential XYZ components. So you get more and more components inside of the CVM, and you want to attest all of them. How do you do this in a safe manner? And your example, a hash, could be anything. Could be a TPM, could be a virtual device, could be anything, right? So it should be easy to extend the attestation report, which is sent over to the verifier to attest it against a specific remote attestation service. So yeah, all of those things are planned somehow, but someone needs to implement it. And if we have the right use cases, we can work on them and enable them upstream for other use cases as well.
Okay, great question. I have one question. This is kind of looking for advice to see how do we do this. As you said, it's like each parties can define their computational computing policies and to say, can you give me your evidence and then verify against the policy I defined.
Mm-hmm.
But the question is, how do we even guard the policies of somebody not being changed? Like, for example, you have a policy, so you must have the H100 GPU with whatever the versions, and then, but you set it up, but I decided somebody modified it and say, hey, don't check them, and then all the setups, all the CC setups, they become obsolete, right? So because you simply let anything goes. So how do we prevent that? So do we that policy itself being put in some secret key vaults and then release? I don't know where, because this policy is supposed to be check against, the verifier to check against, right? Yeah. And not tempered. So where I put that?
Right. That's a good question. That's what we're currently also discussing, how to bootstrap your confidential cluster, right? So how do you bootstrap it, and how do you make a trusted pipeline? The other thing is supply chain security, right? You want to make sure that all the things that you build are coming from a trusted source. So this is also a thing that we are currently discussing upstream. But let's get back to the bootstrapping stuff. Usually your verifier and KBS and policies are on the tenant side, where of the relying party, right, which is the workload owner, and not on the cluster where you're running it. Because trustee can be seen as a remote attestation service, and this remote entity needs to be somewhere in a guarded entity. So what you could do is run those containers as well in a confidential environment, and you could also say, okay, only if my hardware is attested, I'm going to enable my trustee or my verifier to run on my tenant side, because I don't trust other teams, doing any harm on my policies. So you could run all your remote attestation services as well in a trusted environment or in a DMZ or whatever else. And again, you can apply the very same principles here, attestation, and then releasing the secret into. But then you're going to say, okay, but how I'm going to protect the other party that's attesting my. So there, I mean, it starts somewhere. You need to start trusting someone at some time, right? It's like secure boot, right? Firmware starts up. This part needs to be trusted, because when the firmware starts up, which is doing the measurement of all the other pieces and doing the TPM register extensions, right? Doing the measurements in the TPM registers. So this part we need to trust. So we need to start trusting somewhere, somehow. So you need to protect your attestation service on the tenant side somehow, somewhere. So yeah, but that's a good point. You are attesting, but who is attesting my attest, and who is then attesting? So you can go forever, but you need to start somewhere, trusting someone at some time.
Yeah. Any other questions? I'm asking other questions. Anybody else has other questions?
Actually, I have a quick question for you. Compared with traditional containers, this Kata thing, what's the performance penalty? I mean, if we're talking about the similar or the same devices like CPU and a GPU running the same app in the conventional so-called non-confidential insecure container versus so-called confidential container, what would be the performance penalty, if any? I'm kind of imagine a lot of encryption, decryption, those kind of things. They add security, but also they introduce performance penalty. Any idea how big or how bad that is?
Well, as a performance engineer veteran, I need to say it depends, right? It really depends.
Okay.
No, but let me just elaborate a little bit on that. All right. So with bounce buffers, we are limited by the capability of the CPU to do encryption, the encryption engines on the CPU, right? So if you have a lot of I/O between the CPU and the GPU, you will see some performance degradation, right? But if you're doing like compute only, you will not see any performance drops. Well, maybe some latency, some startup we're doing some configurations, but the workload inside of the GPU is running unencrypted, right?
Okay.
It's only when it leaves the CVM, the confidential VM, where encryption starts. So if you're running
the I/O part of it you're talking
I/O
about,
part of that, that's where you're seeing some performance degradation. This changes with Blackwell because it's on the PCI Express bus, and this would be line rate encryption decryption. So you essentially don't care, because the CPU will just say, okay, yeah, it's here. Kick off this transfer to the GPU, and the PCI Express will take care of all of this stuff. So all the mechanics that I explained here will happen on the PCI bus at the station, all those components, and then it will kick off like at line rate what the PCI Express bus can deliver. So yes, if you're doing a lot of I/O, you will see some performance drops. But on the GPU, if it's 100% compute, nothing.
Well, another question that, if I may, you mentioned in previous slides something about homomorphic encryption. This is where I got a little bit confused. How is this compared with a CC? I mean, we're trying to get rid of it because that damn thing is very slow, very memory hungry. My assumption that with a CC, we will never have to need that anymore. But so from your slide, that is built into the confidential container.
No, this was just just an example of other isolation techniques or multi-party. So there are other techniques, to fortify the isolation between parties who are doing right.
So you got me scared. I said we want to get rid of that thing now.
Yeah. No, this was just an example of other techniques. No worries about that. But I've seen some companies building ASICs for that, that are claiming a tenfold increasement on performance on that. So I don't know what the story behind that is, but yeah, it's full homomorphic encryption is pretty slow, right?
Usually 1,000 times slower. Usually.
Yeah.
In our federated learning applications, we've been trying to use either full HE or even partial HE. I mean, they're all slower, and then they are clear the operation. Some of them are, computationally prohibitive, and memory usage is like very big too, too big sometimes to use it. So we're looking forward to this COCO, the confidential container, this technology. We're really looking forward to it, applying that into FL applications. I think it's going to make a lot of people happy, and also make the app development a lot easier.
Yes.
Because no code change, no code change required, as you said, right? That's a very, very important thing.
Yeah.
Yeah, take several months converting some existing, machine learning algorithm to using certain type of homomorphic encryptions.
Yeah. And not everybody's happy. Some of the customer already signed that. They just can't use it. It's too expensive computationally and memory-wise. Thank you so much. This is great stuff.
Yeah. Any other questions? No, if not, let's just thanks Zvonko again. This is a great talk. There are a lot of insight. Thank you so much. We'll see you guys next time.
Thank you.
Okay, bye-bye.
Thank you.
Thanks. Take care. Bye-bye.
Bye.